Good morning, everybody. Kind of wanted to give some top-level information and details on ADCS today. There's a bit more detail in these slides. I don't want to go through every bullet point because it's kind of dense, but they're online so you can look them up. What is ADCS, right? Attitude Determination and Control System. Sometimes we refer to this as guidance, navigation, and control. Usually that includes propulsion and you're dealing with orbital changes. ADCS is literally how am I moving and positioning my spacecraft. It really is two separate concepts, right? So you have attitude determination, which is talking about an orientation relative to a coordinate frame. So we talk about frames all the time when we're doing ADCS. And we use sensors to provide you information about what is your attitude. And we'll get a little more into that. Attitude control then is the other side of things where you actually use actuators, things to move you and change your momentum, and a control law, which some of you may have studied or started to hear about. And that angles your vehicle where you want to look. You're trying to figure out how you're oriented and how to point in inertial space. And that's really key when you're doing the mathematics. Again, we really won't get into those details here today. But right, Newton's laws work in inertial reference frames, so non-rotating. Unfortunately, you are rotating usually with ADCS, and so there's a little bit of extra kinematics that we throw in to do it. So that can get a little confusing, but yeah, that's what we do. So that's ADCS. Just diving in a little bit more, attitude determination, right? Figuring out where you are. We have a lot of different sensors that measure this, but we also take those sensors inputs and then use software that we do for determination, and we call that estimation of your attitude state. And usually what we're doing with that is using the physics of the motion, and we're predicting what the physics should be, and we're also taking sensor measurements, and you take the best guess of those two sets of things combined. And if you've heard of like least squares error or methods, that's a method to estimate your best guess. In this case, attitude. But Kalman filtering is probably the most extensively used one. And while it's complex, it takes a little bit, usually grad school to get there. Once you get it down, it can be pretty robust and is not particularly difficult with some practice. And then there's other estimation methods as well. Attitude control then, right? Actuators, these are things that maybe reaction wheels or whatnot, but we also use software then, which is essentially our controller, and it uses the estimated attitude as well as the user input, you or I, where do we want to be looking or pointed, or how fast should we slew? And then it controls your spacecraft to get you there. And you're usually looking at your rates. That helps you a lot. There are different types of control methods. Most spacecraft, if you have control, are running different types. So you can't usually design just one controller. So B dot, that's magnetic field. You're essentially pushing against the magnetic field. That helps you slow down as you're tumbling, like say out of the canister for the first time. But proportional integral derivative PID control, that's often used for pointing, LQR, Lyapunov. There's a variety of others that are a little bit more advanced for higher accuracy pointing. So we may use one or all of those depending on the scenario at any given time. Okay, so that's the top level stuff, and we're basically diving into the rest of this over and over throughout this presentation. You can find tons of references and literature on this if you want, but we talk about this oftentimes in a control loop. Usually by sophomore-ish, maybe junior level, you've probably seen this type of diagram before from your dynamics classes. This effectively shows you all the major steps. So if you kind of follow my arrows here, the key, right, is the blue boxes are essentially physical things, and the gray are software that's running to do this. So we have our reference attitude here, and this is essentially defined by you and me for what do I want my spacecraft to be doing. And we difference that with where we think we are, the reference attitudes estimate. And the error between those two is what drives your whole control law. And so you may have an attitude controller, you may actually have a lower level actuator controller that does the physical control of like wheels or torque rods or things like that. And then you have the physical dynamics of the actuator. You have your external forces and disturbances. And finally, you have essentially your spacecraft itself, and we call that the plant. I'm not actually sure why that terminology exists, but either way, that's the plant. So that's essentially the thing that is representing the spacecraft mathematically. Then we have our sensors, we use our estimation, and then we can go back and actually do this difference. So this whole thing is running perpetually in your software. You may be running it at 1 hertz, 10 hertz. It sort of varies depending on how accurate you need to be. So this is the top level diagram of what we're doing, the different chunks of software that we may have, as well as the different chunks of physical items that we have. People can spend whole careers just being like awesome at controls. People have spent whole careers just figuring out how to do determination better. Like a guy named Kalman worked mostly on that. The hardware is stuff that we could build. So yes, there are people who also just work careers making really good hardware. So all of these things can be very deep, good technical topics. Let's jump into sensors. So effectively, the rest of this presentation, we're going to talk a bit about sensors, a little bit about determination, and then same thing, controls, actuators, and then we'll have a few other notes. We're hoping to give you a few examples here and some things to think about. So, right, given a sensor, what does it do? Why are we using it? And other things just to think about when you're potentially picking these sensors. And so the rest of the slides on each of the hardware items are outlined this way. So a magnetometer measures Earth's magnetic field, or any magnetic field. So if you have magnets on board, or you have a magnetically noisy environment, potentially due to power switching and up conversion and down conversion, things like that, magnetometers will measure all that for you. We use this a lot on CubeSats, and we use this a lot for low Earth orbit because in combination with torque rods, which are your actuators, you can reduce the momentum in your system, which is an important thing, and that helps you essentially perpetually stay stable in your system. These are your key sensor when you're doing your D-tumble maneuvers. So when you're running B dot, this is literally measuring B, the magnetic field. And so you're pushing against those things. Can be damaged by exposure, and then you can see yourself in other components as well. So these things can be kind of challenging to use. If you have science that you need to measure magnetic fields of like Earth or planets or other things, you oftentimes actually extend these out on a boom just to get cleaner measurements. That's a magnetometer. Your gyroscope. This guy is like the main thing that you really care about, and no attitude system is basically complete without it. So it measures your angular rates, essentially how fast am I spinning in any one direction. And this is important because you can take this and then with dynamics essentially propagate forward your motion. So your gyro is essentially what tells you where am I going. And yeah, so these guys are incredibly important. We often are using low-level MEMS type components, but you can get really high-end fiber optic gyros, ring lasers, other things like that. Submarines use these with high precision to make sure that they're tracking and moving forward correctly. Again, they're propagating their motion based upon what they're measuring their roll spin rates to be. So these really matter. Really cool ones that I've actually seen, you can sit on top of a desk and they will actually measure Earth's rotational rate, just like sitting on the ground. So yeah, you can get them more precise, but you can actually still measure them on the ground. The stuff that we use usually in small sat land is not going to be that precise, and that's okay, but they can be pretty cool. And there's a lot of noise and other stuff that we have to deal with here, so that's part of our estimation algorithm. Okay, sun sensors are another really key thing that essentially tells you where's the brightest object in the sky, the sun, and that helps you point your solar panels that way. It is sensing the direction of a bright object, not necessarily the sun, but you can limits and thresholding to determine if it's the sun or not. They're usually not particularly accurate, but they do okay. And yeah, you need another sensor, obviously, while in eclipse. Otherwise, you don't know where you are while you're on the dark side of the Earth. They can work better when you're out at like geosynchronous orbit or other deeper space places. So we use this mostly like when your spacecraft's more in safe mode to just determine where's the sun, get my panels on that, generate power. They're very simple. Usually they're like literally photodiodes. They're such tiny little solar panels, and you can measure the voltage curve across that. And so as this photodiode essentially rotates off of the sun, you can measure that angle essentially based upon the voltage curve. So you can build these as well at home. Star tracker. We're getting a little more advanced here. So this essentially takes a picture of the night sky, and it will map out bright stars it sees, and then it will use that and reference it to a catalog of stars that humans have made, and it will essentially say my best guess for where I am rotated, these few points of stars, and this means I am rotated or clocked at some angle about that. And so this can give you quite accurate attitude state. So as we state here, maybe around 5 arc seconds or better when you're across the bore sight, and about 15 arc seconds down the bore sight. CubeSat level, that's about right. We can actually get better with slightly bigger star trackers on larger spacecraft. Arc seconds, if you're not familiar with that, there are 3,600 arc seconds in 1 degree. These are pretty accurate. These are pretty tight. And this is still even at a CubeSat level, which is cool. One of the big things, you can't be slewing too fast. These will lose lock on your stars because it gets blurry across its camera if you move too fast. So you can't go too quickly while using these at any one time. Sensitive to stray light. If you rotate too fast, they can be sensitive. You need to do a little bit of cleaning and maintain clean assembly integration and testing procedures when you have one of these on board, because you can gunk up the camera. You may have a couple of star trackers if you want even better pointing accuracy, but obviously that adds some complexity as well as cost. GPS receiver. So this is more of the navigation side of things, but it does matter for pointing too. There are multiple types of GPS that we use in space. Oftentimes what we use in CubeSat and SmallSat land is terrestrial-based GPS receivers, and we have to essentially request that they be unlocked to work at the correct orbital speeds. And that takes a little bit of work and licensing to do. It is totally doable. You can do this at a university level, but you cannot fly a terrestrial GPS receiver in space. It won't work. They do that because what you don't want to do is put terrestrial GPS things on other munitions, and now they're GPS guided munitions. That's the important part. So you have to show like, look, I'm cool. I'm just going to use this for a peaceful scenario. And then you can get these devices unlocked. Either way, that's important. It does provide navigation as well as timing information, which sometimes is more important depending on your mission. You may want very precise timing, even if you don't exactly care where you are. Obviously, you have to be in low to mid-Earth orbits. They can work up at geosynchronous orbit, but they are not particularly great. You have to do some special stuff, both with your RF as well as your algorithms to make all of that work. Obviously, you want to have these things sort of pointed out zenith or anti-zenith, right? Along the Earth's poles actually aren't the best pointing. You kind of want to be more out where the GPS satellites are. So that's your more ideal pointing for these. The other thing too, actually thinking through it, you will read in data sheets, they're like 2 meters, 5 meters accurate. That's wrong. When you're in space, they're going to be more like 10 to 20 meters accurate. So when you're making your pointing budgets, I would use more of a 20 meter accuracy. They also can take 10, 20, 30 minutes to do a lock on the first time you power them up, or anytime it's been a while since they've actually seen a GPS spacecraft. Big takeaways here. Design and build the sensors. It's not really practical to build most of this stuff yourself. Ideally, you need to identify your needs, and then you can probably buy significant chunks of this hardware. If you really need a good gyro, but you don't need much as far as sun pointing, right? You can get cheap sun sensors, but maybe an expensive gyro or something. It's usually how you do it is you want to have a good system design, you know those requirements, and then you buy consumer off-the-shelf parts. You may still be integrating low-level parts. So again, building your own sun sensor and photodiode is pretty easy, relatively. Building your own star tracker is kind of hard. And we talk about that here, right? Like it's possible, but there's a lot of both mechanical, optical, and algorithm work to make that happen. So it is doable, but it's a lot of work. So the big takeaway, right, is if you can buy the hardware. Trying to reduce your costs on the ADCS side of things is probably increasing your overall risk for building your spacecraft, because it does take some level of expertise. And you as students can totally get that expertise, but probably by the time you get it, you're about to graduate. So unless you're really sticking around for grad school, that if you can buy. Any questions on sensors that you guys have had so far, or maybe something I didn't cover before we jump into actuators?
I just want to know, like, in what scenario, like, is it appropriate to like only use potentially like one sensor? Or, like, is there any scenario in which like you don't need a combination of all these sensors, or does it just depend on the level of pointing that you require? Or, yeah.
That's a good question. So if you think about this, and I want everyone to do this experiment right now, so you're all going to look silly together, but if I can get one measurement and I know where the sun is, right? So that's essentially a vector in space. So if you stick your arm out and let's pretend you're pointing at the sun. Great. I know where that is. The problem is you can roll about that vector. So I still have 360 degrees of ambiguity in where am I pointing. So you always need a second measurement point to be able to lock in and know how I'm oriented. With that said, you need two independent measurements to know your attitude. If you don't really care about knowing your attitude, then yeah, you don't necessarily need all these sensors. Most systems we fly, if it's 3-axis stabilized, right, you're going to have a pointing set of things that you're going to do that will have usually sun sensors, rate gyros, and magnetometers. If you need better pointing, also star trackers. So yeah, we usually end up flying all of those simultaneously. And they're kind of used in different scenarios, but also you use them sort of simultaneously. So I don't know if that helps, but yeah, they're for fairly simple missions as far as attitude determination is concerned, you can be pretty simple in your measurements.
Yeah, does it ever make sense to use your solar panels as a coarse sun sensor?
Yeah, you can. I haven't really seen that too much because I think mostly what it does is you have to put all that sensing now in line with your power generation. Feels like we just don't do that because it's kind of a complexity issue. It's just easier to stick on a smaller like photodiode and just measure that directly and do all your math without also trying to essentially get power off of that. We don't do that actually a whole lot. The other thing too is if you have one plane of generation, that is not good enough to determine where the sun is, right? You need at least a couple points of your photodiodes to be able to say if the sun is behind me, I can still spot it and rotate around to point my panels at it. So that's the other big reason why we still just use photodiodes.
I just had two questions. One would be, if we were pointing at the sun, what would spell out the difference between being able to use coarse sun sensors and a fine sun sensor? What kind of mission requirement would drive that? And then the second would be, if we're counting on a couple of frames of reference and we're in the eclipse period without a star tracker, I think you mentioned there are some other options, or are there any other options, or do any of those make sense for getting that second frame of reference?
Coarse sun sensors are effectively for safety, right? As far as know where the bright object is, point your panels and get power generated. That's all they really do. Fine sun sensors are usually better tuned. You know your characteristics of those photodiodes much better. There's going to be quite a bit more estimation behind where they think the bright object is. You might use several in combination to get a real vector for the sun. Those are usually accurate to 5 to 10 degrees, maybe a little better. They may state they're a bit better than that. That's kind of the difference. So yeah, you totally can use fine sun sensors. But yeah, the coarse ones are just these broad, like, where's the bright object anywhere in my field of view? And the coarse ones are like, the fine ones are like, cool, now that I have it, I can point a good bit more accurately. They're kind of two unique use cases.
If I had a really strict power budget, would it be, like, you think, very important to have a fine sun sensor that's well calibrated?
Yeah, I mean, I guess you could use it that way. So, right, if solar panels roughly fall off like a cosine wave. So when you're straight pointed at the sun, so your normal vector is parallel with the vector of the sun. That's essentially 100% generation, right? I mean, obviously you have your efficiencies and stuff, but you're gathering all the energy you can. And so it falls off as a cosine. So as you go, it takes 30 degrees before you've dropped, what is that, by half, right? So you can be pretty grossly off before you really even notice a whole lot of power degradation. So if you're 10 degrees off, you probably don't fully see that in your power generation curves, which is nice, right? There's a little bit of flexibility there. What was your second question?
Just about during eclipse, you had said there were some
Oh,
other
yeah.
options. If you chose to not go with a star tracker, what would you use?
It depends on how accurate you need to be. This is one of the reasons why I use a rate gyro. So if you know where you were pointed, like between sun and Earth's magnetic field, and then you go into eclipse, you will keep using Earth's magnetic field and the rate gyro to essentially sort of propagate your motion on the backside. So you may build up error over time. You can make it to really not be that large, probably a couple of extra degrees. The star tracker will keep you accurate the entire time, so long as it's not blinded. Okay, same type of thing. What does it do? Why is it used? Other considerations. So the simplest version is how we're starting. So passive magnetics, like literally a magnet in your spacecraft. We have flown many spacecraft this way, usually in your 1U, 2U size spacecraft. This is not a bad way to go, just because you don't have a lot of space or power to do other stuff. Permanent magnets, right, will align you with Earth's magnetic field. So acts sort of like a compass needle. And so as you orbit, it's just they're trying to go to magnetic north and south. And so they'll kind of hold that. So you'll get a little bit of sloshing motion. If you're a polar or near polar orbit, the magnets will potentially sort of wrap around. And so you may actually do a little bit of a tumbling motion as you go around Earth if you're in a high inclination orbit. We usually add some magnetic hysteresis material to damp some of that motion, right? So you're not just kind of perpetually like sloshing back and forth. You may move, be a bit more stable that way. These things can be really nice if you don't have a whole lot of exquisite pointing needs. You will be aligned 15-ish degrees with whatever local magnetic field. There was one student mission called CSSWE out of LASP and Boulder that they flew these on, and it worked pretty well. But they were measuring magnetic field and some other stuff like that. So they were good with that type of coarse attitude. Torque rods, torque coils. These guys are electromagnets, and we essentially put a current through a coiled wire. And if you remember, like your physics 101, right? If you have current moving, you can create a magnetic field. And so depending on how they're constructed, you can actually amplify this effect or make it more effective. And that's essentially what a torque rod does. The cool thing is that they're really mechanically simple. Once you build them, it's literally like wire wrapped around a permeable material. And you can push current one way or the other through it and get your magnet going one way or the other. And you can do little bits of current, lots of current, and actually scale your overall input to the system. These are really nice. You will probably end up at least flying torque coils or torque rods. They are pretty good for pointing, but you're going to get into a 5-ish degree pointing capability with these things. And partially that's just because they're not that strong of a torque generated. And so you can't just like slew this thing around and point at all the stuff. You're slowly nudging your spacecraft over time. So yeah, you can do okay pointing. The other big thing to think about with torque coils and rods is you're in what we call an under-actuated system. So the problem is they can only torque about the Earth's magnetic field, but because that is a cross product, if you think about cross products, it's always zero parallel with that vector, the Earth's magnetic field. So we can only generate torque on the other two directions. So that third direction, we can't ever really do anything there. So that's what makes it under-actuated. You only have 2-dimensional control, not 3D. And so you're not a true 3-axis stabilized system. You can't really control the spinning about the Earth's magnetic field line. And that depends as you go throughout orbit, right? So as that changes, you can still sort of control the spacecraft, but it's still not fully 3-axis controlled. The other thing that we actually use these for all the time is what we call momentum dumping. Magnetometers and torque rods essentially constantly allow you to push against the Earth's magnetic field, and you can pull that momentum out of the wheels and essentially draw them down over time. Most three-axis systems that are in low Earth orbit will use torque rods continuously to continuously dump momentum. Because of that, if you have reaction wheels and torque rods on a CubeSat or SmallSat, they're actually very nimble platforms because you sort of have infinite momentum capacity since you can constantly dump it into Earth's magnetic field. If you're going above mid-Earth orbits, you can't use these because the magnetic field is just too weak, and that's when we have to use something like thrusters and propulsion. We can get a little more into that in a little bit here. But anyway, you're probably going to be flying these to some level. Reaction wheels. This is literally a hunk of metal that is balanced, and we stick it on a motor and we spin it. And so you've probably seen these in physics demonstrations too, right? The bike wheel or whatever. And so you essentially have the wheel spinning, and the more you try to spin it up, the more equal and oppositely it will rotate the spacecraft. And so you're essentially exchanging momentum between your spacecraft body and your wheel. And that's all they're doing. So we usually fly at least 3-axis control. Sometimes you will fly 4. That adds some redundancy and overall capability. These things can be fairly expensive. However, we're talking like tens of arc seconds of pointing accuracy if they're well balanced. You can actually make a 6 or 12U CubeSat point really well. It's actually really cool and awesome how good these little platforms really can be in terms of all this. If you need higher precision pointing, if you need to slew, these are probably your actual option. There are some issues. They will be perpetually spinning. You don't want to actually have them at 0 because you get a little bit of weird dynamics when you're trying to get over that hump of inertia and some of the motor dynamics. So we actually bias them like plus 100 or negative 100 RPM or something like that. You don't actually try to hold them at 0. Eventually you saturate, so you need to constantly dump momentum or let them get close to saturation and then get rid of all of that, dump that momentum with thrusters. Reaction wheels also are a wear out mechanism. Eventually they will break. We have not generally seen that in CubeSat, SmallSat land, because usually our spacecraft lifetimes are shorter than the reaction wheel lifetimes. And so we have not generally considered these a limited life item. But Roger Hunter, the guy from NASA who talked a couple of weeks ago, he was talking about Kepler. Kepler actually lost one of its reaction wheels after years of operation. And that's one of the reasons why they couldn't keep operating it, is because it didn't point quite right. But we don't see those problems generally in SmallSat land. This is just a silly YouTube video, but this is reaction wheel spinning. So this cube is literally balanced on its corner because it's generating enough torque to be stiff to motion against it. So yeah, as you can tell, reaction wheels totally work. It sort of feels like black magic, but yeah, this is how we spin our spacecraft around, and you can change its momentum and yeah, make it do some kind of crazy things. Control moment gyros. You will probably not use these, but we're just going to throw them in here anyway. So they're the same idea as a flywheel, like a reaction wheel spinning about an axis, but instead of spinning it up and down, you actually keep it at a constant rate and then move the whole body of that. So if you guys have done the bicycle wheel example in a physics class where you spin it and hold it on a swivel chair, and then you try to move it, not only is it hard to move, but you actually will spin too. That's a control moment gyro. They're high torque, which is really nice. So the International Space Station uses these because they're so high torque, and the ISS is like this huge thing that needs it. You won't really see these. I don't even know if we have these things on the market for CubeSat class. I don't even know if most SmallSat class size spacecraft even have these. I wouldn't worry about them, but just trying to make sure you guys are aware of them. They are useful for really fast snap control needs. I think there was a mission that NASA flew. I think they used CMGs where they were actually trying to spot nova, like supernova events. And so they catch a bright flash and then snap the spacecraft over and observe it as much as they can. So that was like a really fast maneuver that required something like this. Thrusters. Obviously, thrusters help you maneuver. They can maneuver you for orbit. They can also help you dump momentum and pull momentum out of the system. There's two big types. You have your chemical propulsion, which is high thrust, generally low efficiency. And you have your electric propulsion, which can be low thrust, but high efficiency. And what we mean by efficiency here specifically is fuel use. So you get a lot of thrust, but you burn a lot of fuel quickly. Electric propulsion is the opposite of that. There are some systems that do dual use for like orbit control and attitude maintenance. You can do that as well. If you think about this, if you're trying to just do orbit maneuvering, your attitude system can hold you in whatever direction you want for your thruster, and then you can thrust to change your orbit. If you're using your thruster to dump momentum, you need at least 3 of them to be able to pull energy out of all of your wheels. You need enough to cover all 3 axes, essentially. The big thing here is, while it's technically possible to use thrusters for attitude control, it's not recommended. NASA has done this for like Marco and some of the deep space CubeSats. There have been both some success and failure, and that's just because right now propulsion is still a pretty challenging subsystem for our spacecraft. We're still struggling with getting the technology right, our procedures. Cleanliness really matters for your process for how you build, clean the system, and actually put in your fluids. We gunk up the valves all the time. So this is still I would call it an emerging technology, although it is getting rapidly better, but we still have challenges with it. So just be warned, if you're like, I need thrusters, that may be a major mission risk for you guys. Designing and building these things. Magnetic torque rods, coils are generally pretty easy to make. I've actually helped make them back when I was a student, so you can build them yourselves. It does take a little bit of time. You probably need to make a few before you really get it down, but they're fairly cheap, fairly easy. But you can buy them too. Reaction wheels are tricky, but possible to make. You do need fairly balanced stuff, so if you have good machinists, a good machine shop, it's doable. This one takes a little bit more work. Don't even think about making CMGs or your own thrusters if that's part of your primary ADCS. Obviously, if your experiment is doing thrusters, great, give it a try, but you should not be relying on them to be fully working and dependable. All active control requires algorithms and software to actually do stuff with your actuators and sensors. The design actually of these can be relatively easy, but the actual implementation of it between your code, testing of it with your hardware is pretty challenging. And that's at least grad level, usually even beyond that. The bottom line is, be careful here. You can do it, but be very aware of how challenging this is. You will need a pretty rigorous staffing program to make sure that it doesn't stagnate. And you're going to need some good people on these to make it happen. So this kind of goes back to, if you can buy it, that's probably a better place to spend money to buy down risk. And maybe you can build some other parts of the spacecraft. We ask a lot of these fundamental questions, and you will hear this type of information in exchange if you continue to work in the space industry a lot. So what is your absolute pointing accuracy, right? How well do I need to point? What is your absolute pointing knowledge? How well do I know where it's pointed? Those two things are different, unique, and matter differently per mission that you may have. We definitely have some that care about pointing accuracy, but really what they want to know is, where am I pointed? I don't need to be super tightly pointed. So those can be very different driving requirements. We have this other thing we call pointing stability, and that's essentially how well does it stay on target. Jitter is how shaky is that, and jitter can be a really fun but challenging analysis because it then includes wobble, let's say, in your reaction wheels. If they're not perfectly balanced, which they never truly are. But other things, like if you have deployed solar panels, so now you have a floppy spring mode, or if you have a deployed boom or other things, that all adds flexibility to your system. And so now you can kind of be a wobbly structure in space. And if your reaction wheels or your motion happens to move at the same rates that excite those modes, you can start to really bounce around in space. We can also design around this, but that's kind of jitter for you, as well as elements of pointing stability. And then also there's slew rate. How fast do I need to point to a new target, or how fast do I need to track something, or those types of things. So slew rate also matters, and this jumps into your controllability. But those are the top level questions. If you haven't asked yourself, that's things you want to get into. Some of these might be like, I don't care, and that's a fine answer. But depending on your mission, you may really care. Taking those as like your driving questions. You can kind of ask those based upon the different elements of your system. So much of the summer is about learning the interconnectivity of all of these. That's one of the big things we want you to take away. So obviously your payload is probably your key driver. That's why we're mentioning it first. But what is your pointing accuracy to put like a camera on target and look at a star or at the ground or whatever? Do you need pointing knowledge and position knowledge to characterize your response to geolocate data? Optics also have a maximum allowable jitter to prevent your blurring. Communication systems can really matter, especially if we're talking laser comm, right? UHF is very forgiving. S-band is pretty forgiving. X-band's less, KA is less, and so on and so forth, right? So your comm system and antenna pointing requirements may drive some of this. Power. Obviously, you need to point your panels to the sun. If you have many panels on your spacecraft, those requirements may be much looser, or they may be fairly strict. Here's a good number, right? You have a 3% loss in energy generation at 14 degrees error off the sun. And that's essentially just your cosine function, like literally cosine of the angle. And then obviously your overall ConOps. Do you have sufficient slew rates to switch between modes within times that matter? If you think about our ship sat example, right? When it was trying to slew to look at all the different like docks and bays or whatever, that was kind of like a ConOps slewing requirement that we had here. A big one, right? You need to factor in detumbling and the time it takes to do that. How often might that occur? A key observation, CubeSats especially, but essentially all small sats tumble at least once in their life. And that's when you get deployed. Usually if you have hiccups and resets and other stuff, you may end up tumbling again. And so you need to be at least somewhat resilient against that event. So requirement flow, top level drivers, right? I need to point the camera for ships out here to within half a degree of the target, figure out what the driver requirements of that is. It's like, okay, well, what that means is if I have half a degree of absolute pointing, I might need to know where I'm pointing to within 0.1 degrees, right? My knowledge here. So now you can start to have an error and real pointing budget breakdown and stack up. Can I find solutions that meet those requirements, right? You kind of do that iterative loop, which you guys are definitely working right now. And then check your other subsystems. Fields of view, right? Do my antenna fields of view all align the way I need, right? Is down towards Earth? Is GPS pointed out towards space and not towards Earth so I can see the GPS satellites? Those types of things. We kind of have talked about this a little bit, but you write requirements for either what your mission needs and see if you can find capability to meet that, sensors and actuators, or figure out what actuators you actually have and bound your mission into that scope. So you may have to cut stuff down to be able to meet what attitude control is capable of. So analyses and testing. Your pointing budget really is based upon those top level questions and the accuracies you need and stability and stuff. It's like, what do you actually need? What system gets you there? CarSat's a good example of doing that derivation. We also have a lot of disturbance torques in orbit. So solar radiation pressure, like literally the sun is outputting particles and matter, well, that will hit your spacecraft and literally try to push you around. It's a very low overall force. And so when you're below about 800 kilometers in altitude, so low Earth orbit, atmospheric drag, the next thing we mentioned, really dominates, right? The atmosphere, even though it's very thin, still is your driving torque in orbit. Once you get above about 800, 900 kilometers, solar radiation pressure starts to take over. And that is actually the key driver out at like geosynchronous orbits and beyond. Atmospheric drag, it does matter. The more symmetrical your body is, the less it probably matters depending on what attitude you have relative to your velocity vector into the motion of like where it's the air hitting you. What residual magnetic fields you may be having or generating that can torque you if you're close to Earth. Gravity gradient torques, not a big deal on small sats, but can matter for larger structures. So like Hubble Space Telescope, the space station. And you want to check all those things relative to available control authority. So essentially your torque rods or your thrusters generally should be bigger than the summation of these torques, because if you can't compensate for them, you won't be able to, in the long run, essentially remove them from your overall dynamics. So we can talk about details and finesse there, but in low Earth orbit, again, drag is probably the big one. You're creating like micro newtons, tens plus of micronewtons of force at any given moment. It's pretty small. It's usually pretty doable to overcome those things. If you have a periodic event where you're pointing away and drag is lower, and then you're back doing lots of drag with like solar panels in the sun or whatever, that won't really build up momentum over your system because you're just sort of like balancing out those events. If you're constantly keeping some attitude, that may help you generate momentum build up over time because you're not sort of balancing out like your different attitude states that can like positive, negative, and balanced stuff. It turns out it's incredibly hard to actually know if your ADCS system will work when you're on the ground and through ground testing alone. So what we have to do is lots of physics-based simulations to determine the performance of your system, even if you're buying consumer off-the-shelf parts, like you're buying CubeSpace, Blue Canyon, what have you. So you need to build up a simulation environment on top of getting the hardware and putting it together. So estimate or guess that your attitude knowledge needs to be 5 to 10 times better than your control capability. So if I need to point to 10 degrees, what we're saying is you need to know that to about 1 to 2 degrees where you're pointing. So yeah, it's a 5 to 10x. And that's essentially knowledge is the input to control. You can never control better than where you know you are. And if this matters when you're doing simulation, right, if you've heard of this, there's Runge-Kutta methods. Those are usually good enough to model your attitude dynamics, and you can use those types of integrators to do this. There can be some issues, but either way, at the top level, that's a pretty good way to go. So testing, we highly recommend doing polarity testing, and that's literally like if I hook up my reaction wheel, when I say I want it to spin up positive, is that in fact positive and negative is negative? You could easily screw yourself up where if you literally just plug things in the wrong way, do I physically, electrically have things connected properly? And this is true for your sensors as well, right? If you think the vector's this way, but it's really that way, that could really mess you up. The other part about that polarity is checking to make sure that all the code in your software is correct. So that, yes, I'm commanding positive, and it is in fact spinning it or measuring it as the direction I expect. That's all really good, simple checks, and that kind of helps you debug and get rid of dumb mistakes that will really mess you up on orbit. Just verify that you have reasonable values of your sensors. You don't need to go to the nth degree to make sure everything's good, but if you have your magnetometer, can I measure Earth's magnetic field? Does it look about right in the about correct direction? Okay, great. We literally may take our sun sensors outside and say, yep, we have a bright object, or maybe we'll just take a bright flashlight and point it at it. Those types of things to just sort of at the top level, like, is it getting the values I roughly expect without going super deep? Hardware in the loop testing is also incredibly important. Most COTS systems come with simulators to help you verify the overall functionality of the system, and they may help you plan out some of your concept of operations. They're not a full end-to-end test, but they really help you just like debug and kind of vet the system. By the way, if you're interested in this topic as like grad students and whatnot, you'll probably spend a lot of time doing one or both of these types of things. They're pretty deep and can be a lot of fun and interesting. Final bits of considerations here. So error stack up. This is part of your pointing budget, more or less, right? Your system level requirements specify performance, obviously, but not how you achieve that. So you must sort of parse out what your different components and sub-elements, how much error they're allowed to have. And that can be with respect to how good is your sensor, how well is it aligned, does it vary over temperature range, those types of things. And so what you want to do is take your best guesses or knowledge of those and analyze and kind of do a stack up of all of those errors. And that can give you essentially your tolerance to your pointing budget. This becomes a very tightly coupled process between your hardware and software. So some of the software may help you get rid of some of these issues. It may actually help you estimate some of the biases the system may have, and you can get rid of those. We can talk more about that if you want, but that's kind of a cool process. So here's an example, right? Pointing my payload like shipsat, right? I'm trying to image a ship. Okay, so your base knowledge error, how accurate is the star tracker? Cool. So that's point one. Now I know that my star tracker as well as my imager have some mechanical alignment error to them. So even though I say it's pointed here, I'm slightly off of that. And then those things will flex around as your spacecraft essentially moves with thermal changes. And then you have your algorithm on top of that, your filter for what is your best guess accuracy for those types of things. And so you can stack all that up and still get an estimate for, am I still within the top level requirements I have specified to geolocate that image? Other big things, many instruments have keepouts. Usually this is like, don't point the camera at the sun. And usually it's for damage concerns. So hopefully you buy stuff that doesn't have damage concerns. You may not be able to image while you're looking at the sun, but hopefully it doesn't burn your optics. Ideally, it's more of a functionality issue and not damage. Try to pick things that won't get damaged. And the reason because of that is you and CubeSat and generally smallsat land cannot unconditionally guarantee that you will maintain keepouts for the duration of your spacecraft life. You will probably tumble with a reset, and so you have no idea if you will potentially point your cameras or other sensitive equipment at the sun or the earth or wherever. You can put lens covers on, you can do stuff like that, but if you have a hiccup and a problem later down the road, which you're probably going to have, it's hard to guarantee anything. Just keep this in mind. How does this work? Try to pick equipment or be cognizant of equipment as you're looking for keep out concerns. And this also matters for alignment, right? Your star tracker can't look at the sun and get star tracking. So make sure that is not pointed at the sun while you're trying to do precise imaging on Earth. Like make sure your star tracker is away from the sun. So fields of view and mechanically designing the system can really matter for this. And actually, that's what I started to get into here, right? Just making sure you actually have good geometry. Other subsystems. ADCS is a pretty big power suck. You can do a decent amount of current. These numbers come out of some of the stuff we have worked with. You may get different numbers. So these are WAGs coming from a couple of our experiences. But either way, you can be a decent amount of current draw, and you can peak up fairly large when you're doing slews and other maneuvers, but it won't last for more than a few tens of seconds at a time. So either way, the power system needs to be able to source that much energy and current, but also be able to support ADCS running perpetually in between times too. It can be fairly challenging on EPS. We also can produce a lot of data. There's a lot of instrumentation and metrics that we care about because we're a mechanical system and all of our software processes simultaneously. So it can be a big data driver as well. You may decide to reduce some of that information, but it sort of matters to CDH. Yep, magnetics, you have to be careful here. You can't create your panels to generate power in a loop because then you create a nice big magnet when it's in the sun. And so there are things to just be careful with how you create your solar panels. Avoid certain types of steels, right? We wanted to use like 316 type alloys. Others do allow magnetic, they're more ferrous. And so you will get more magnetic buildup in those, and you don't want that. Obviously, things are pretty complex. If you can buy systems, generally that's what we're recommending. Even if you're doing a top level assembly of all of this, usually that means you're also doing the algorithm and software work, and that is not a small task either. All of this is doable, but just be very cognizant of how much work you may be taking on. So reduce risk by using money for where you can. We don't recommend that in all of the locations for your missions, but this might be one place where it's good to spend. I hope this is kind of a good general overview.
When you were mentioning about 2-axis or 3-axis control, let's assume I did want to go with 2-axis control because I have not a stringent pointing requirement or degree of knowledge required. Are there any weird effects that come out of that I might not have accounted for?
Yeah, if you are under actuated, you can't point in any direction at any given time, right? You can sort of control your pointing, and it will vary over time, right, as you're going around Earth. That's kind of it. And your comm system, what I would say is You just sort of want to think about how, right, because they sort of have lobes where they're good. You want to try to have those to where you may be mostly covering the ground in most attitude states. You're going to have a ring where it doesn't work, but you don't want to have your planned spacecraft alignment such that it's always putting the nulls towards Earth. Think through your fields of view, your geometry. But otherwise, no, I don't think there's any other weird gotchas there.
Are there many CubeSats that actually exploit that disturbance torque, gravity gradient disturbance torque with gravity gradient booms?
Not really. Because we are still just such small form factors. No, it hasn't really come into effect. If you did deploy a boom, the mechanical challenges of said boom, as well as the storage of that, right? You may be using a third of your space just to have the storage of that boom, and then you deploy it. And now that volume, if you will, is sort of unused for the rest of your mission. There's a few reasons why that trade usually doesn't seem to work out. There's been tons of CubeSats launched, so I'm sure someone has done that, but I am not aware of it. It is not a common practice by any stretch. On the bigger missions, when you may still package a boom, but relative to your overall volume, it's not as big of a deal. Other missions can do that better. It's a bit different when you're, especially CubeSats, you just run out of space so fast.
Could you expand on what Kalman filtering is?
Kalman filtering, essentially what it is you have a model based on physics, right? So you're saying, I expect myself to just move in this manner because I know where I am and I know how fast I'm going. So you have your physics-based motion. On top of that, you are also saying, well, my sensors are telling me this is actually my motion, right? Based upon measurements. So the Kalman filter essentially propagates the physics and then takes the measurements and differences those two answers at any given time. And then essentially what you try to do is say, okay, I'm going to try to guess what's the minimum error between those two. And that's going to be my best guess for my actual attitude state. You can do this for orbit position as well. We have estimation for position as well as attitude. That's effectively what's going on under the hood. So both of those are potentially non-linear problems, but when you difference them, you can actually make it mathematically linear, and then you can do like least squares and other stuff on top of that. And so it was kind of a cool trick that Kalman figured out. But yeah, now all that math becomes linear, it becomes much easier, and we have a lot of tools to manipulate it to essentially minimize the error between those two sets of measurements. And so once you get your best estimate that minimizes the error, you take that and you add that to your current position estimate, and you say, cool, now this is where I am. And then your physics take that value and propagate that forward, and your sensors keep giving you data, and then you do it again and over and over. And so you're essentially fusing those two values every time. That's like the top level. We estimate the differences there, and we assume that all the noise and errors that we haven't modeled are Gaussian, right? They follow a normal distribution. That is like blanket a wrong statement most of the time. And so other estimation methods do not make that assumption. And so like Bayesian estimation and others may actually use the distribution we think is error to then create the correct distribution of error to help propagate all of that information forward. Those can handle less linear dynamics or faster changing dynamics or whatever. And so there are other estimation algorithms that allow you to do all that stuff that are maybe better than Kalman filtering. For the attitude determination, you probably don't really care. You should be fine as is, but there are other environments where Kalman filtering just isn't quite the right application.
Thanks, everybody.